Now let's see how to analyze this space complexity. So I want to see about this space. Now till now we have seen about the time, and now I want to see about this space. So what is space is, given a program, how many memory cells are required in order to finish the algorithm or that program, and this has to be analyzed in terms of the given input size, which means if the input given is n, input size is n, then related, with reference to this, comparing with this, what is the amount of space required to finish the algorithm. So do you need an extra cells? If you need an extra cells, then it is going to be order of n, or whatever the size of the input is, you don't need any extra, you need only 10 extra cells. Then I say it is constant time, constant space required, which means just a constant amount of memory, extra memory is required, whatever the input size is. Or if the input size is n, do you need order of n square space, which means depending on the size of the input, with reference to that, what is the size of the total space required to solve the algorithm. Okay, so how to analyze this is one thing, and second thing is, any algorithm, given any algorithm, there is always a trade-off. If you want it to be performing with less time complexity, then you might have to have, you might sometimes have to give more space. That is sometimes. And sometimes if you want to give it less space, then you might have to give it more time. Okay. So depending on what the, what your requirement is, do you want to decrease the space or do you want to decrease the time, we can analyze, we can design the algorithms and we could analyze them. So first of all, let me show how to analyze a algorithm and find out what is the total space required in order to execute the algorithm. And as you know, algorithms are of two types. One is iterative algorithm and other is recursive algorithm. So let me take the iterative version first, explain you about the amount of space required, and then we shall go for the recursive. So we have seen the iterative version and recursive version of algorithms in terms of time complexity. Now we are going to see it in terms of space complexity, which means I am not interested in finding out the time complexity. I'll be talking only about the amount of space. So let me talk about the iterative program. So let us say the program is like this. So some program is having as input an array A whose size is n. So array is starting from 1 to n, which means A is given as the input and the input size is n elements. Okay, and now I am going to use, let us say, int I, one integer I, and then I have a for loop for I equal to 1 to n, A of I equal to 0. Simple small iterative program, right? Now in this program, see, and the syntax of this program is not related to any particular language. It is a generic program, so you can even call it an algorithm. So given the algorithm whose size, whose input is A and the size of the array A is n elements, and now I am writing it to be, with a single for loop. So for the entire program, so we needed n size input and then only one variable, right? So let us say that variable size is one cell. Then how much total space we require? N plus 1, and we are not going to count this n because it is given in the input. Therefore, what is the extra space required in order to run this algorithm is, it is simply 1, right? Let us say we have even one more constant, ij, and here I am writing it as for ij, and then for I equal to 1 to j, let us say j equal to 10 or something like this. Then how many total extra variables that we declared here? 2 variables, right? So whatever it is, the extra amount of space required doesn't depend on the size of the input. So even if the input is 10 or 100 or 1000 or whatever it is, I am always going to use only 2 variables. Therefore the space complexity for this algorithm is order of 1, which means constant. Either it could be 2 or 3 or 10, whatever it is going to be order of n, right? So let's take one more example. Let us say I have an algorithm and which is given A as input, an array as input, and the array contains n elements. Okay, and now in this I have integer I and then integer j, something like this, or let me take integer I, then I am writing it as create, which means I want to create one more array B of size n. So whatever the input size is, I am creating an array which is proportional to that size. Okay, and now I am going to write for I equal to 1 to n, I am simply copying everything from A to B. Understand this? So what I am trying to do is, I have an array which is of size n, and then I am creating another array which is of size n. Okay, and I am copying everything from the given input to B, everything from A to B. Then what is the total size required? So don't count the input, given input. That is not counted as the extra space required in order to, that is actually mandatory. You cannot do anything about this. We cannot decrease it or increase it. We cannot alter it. So only thing we could do is what is the extra amount of space required and how to decrease it. That is what we should think about. So don't consider this A. Think about what is the extra amount of space required for this algorithm. So one thing is you need I, for which one cell is required, and then we need n, B, right, an array B, and whose size is n, which means n. So total amount of extra space required is n plus 1. So the amount of extra space required to solve this algorithm is order of n, right? So this is more. In the previous example it is simply order of 1, but now here it is going to be order of n, right? So this is actually more compared to the previous example, and the amount of space required, extra space required, actually grows along with the with the amount of input given. If the input given is growing, if the input is 100, then I need 100 extra cells. If the input is 200, I need 200 extra cells. If the input is 300, I need 300. But in the previous example, whatever is the input size, the amount of extra space is going to be constant. Let's see one more example. Let us say I have an algorithm and which is given an array A of size n, and now I am creating an array B which is two-dimensional, which is of size n by n, and then I have two integers int I comma j. Then for I equal to 1 to n and for j equal to 1 to n, I am simply copying ij equal to a of I, something. I am copying some everything from A to B, something like this. Then what happens is, see this, initially algorithm is given as the size of n, then how big extra space we require is, we are creating a array B whose size is n square, isn't it? Therefore extra space required for this is n square, and then we are creating two integers I and j, and whose extra space required is 2, right? And then there is nothing here, it is simply using this space and then doing some computation. So total amount of extra space required in this case is n square plus 2. Therefore total amount of extra space or the space complexity for this algorithm is order of n square, which means if the given input is 100, then I need 100 into 100. If the given input size is 10, I need 10 into 10, whatever it is. The input, according to the input, the space requirement is going to increase in the terms of order of n square. So see these three. So first one is, in this case, whatever is the size of the input, I don't require any extra space. That is why it is constant time, right? And in the second input, whatever the input size is, in the second one, whatever the input size is, I exactly require that much amount of time, space, therefore it is going to be order of n. In the third one, whatever is the input size, I actually require n square of that. Therefore this is how we could analyze the space complexity of the iterative version. So iterative version is very simple, you need not work on it much. So the difficult one is the recursive version. We shall see the recursive version now. I'll take a small recursive program and I'll explain you how to analyze the space complexity, and we shall even see how to analyze the time complexity also. See this, let us say I have a simple program a of n. If n is greater than or equal to 1, then a of n minus 1, and again printf n, if this is the case. right? So just see the program. A is a function, and A is taking as input some number n, and if n is greater than or equal to 1. So why is this condition important is, so whenever you start any program, you should know when to stop it. So if I don't have this condition, n can be any. One more thing is, n should be greater than 1. Okay, so we are going to start with some number which is greater than 1, and we should know when to stop it. That is where this condition is used. This is also called as anchor condition or halting condition. Okay, so you are going to stop the program whenever n is less than 1, otherwise you are going to continue this program. Okay, and my assumption is that n is always going to be starting with some number which is greater than 1. That is my first assumption. And moreover, if you see this recursion, A is calling A itself, that is why it is recursion, and then A is calling A right in the beginning of the program. So there are various kinds of recursion, and this recursion is called head recursion. Head recursion means the recursive call is present at the beginning of the program, and the other kind of recursion is tail recursion. Tail recursion means the recursive call could be present at the end, right? And other kind of recursion is body recursion. Body recursion means the recursive call could be present anywhere. So in this program, it is nothing but the head recursion, right? And I'll show you even the example of tail recursion next. Now every program, every function is going to call one more time the same function, right? It is going to call it only once. So how to analyze this is, there are various ways, and every method is popular, but whenever the size of the program is very small, like there are only 3-4 lines in this program, whenever the size of the program is very small, always follow the tree method. So I'm going to show you the recursion tree, and whenever the size of the program is small, you please use this method. If the size of the program is very big, we shall only use stack method. This tree method is difficult to trace out. Okay, so let us say the program is A of 3, which means I want to call this program A on a number 3. Now initially you are calling A of 3, then what happens? A of 3 will get inside and will check if n is greater than or equal to 1. Is 3 greater than or equal to 1? Yes. Therefore it is going to call this one and execute these two lines. Therefore A of 3 is going to call A of 2 by A of n minus 1, and then printf 3, printf n, right? So A of n is going to call A of 2 and then printf 3, and again A of 2 is going to call A of 1 and then printf 2, and A of 1 is going to call A of 0 and then printf 1. And what about A of 0? So whenever this function A of 0 is called, 0 is greater than or equal to 1? No, the condition fails, therefore this is where we are going to stop. So this is the point where we are going to stop, right? So in order to execute the program on A of 3, how many recursive calls we need? 1, 2, 3, 4. Therefore we need these many 4 recursive calls. So if I have A of n, how many recursive calls I might need? n plus 1, isn't it? So for this one, how many recursive calls are required? N plus 1. If you didn't understand this, maybe you can take A of 4, you can take A of 2. See this, in order to execute A of 3, how many recursive calls are required? 1, 2, 3, 4. Or how many times A is being called in order to compute A of 3 is 1, 2, 3, 4, right? So in order to call A of 3, 4 times A is called. In order to compute A of 2, how many times A is called? In order to compute A of 2, 1, 2, 3. Which means if I have to compute A of 2, then I needed 3 calls. In order to compute A of 1, how many recursive calls I needed? 1, 2, right? Therefore, in order to compute A of 1, how many recursive calls are required? N plus 1, right? And let's see how this recursion works and what is the order in which these functions are called and what is the output printed. That is important. Okay, so in order to analyze this, we need a stack. So all the recursive calls of A will be actually pushed onto this stack, right? So initially you start from A and you traverse the tree top to down, left to right. On the way, whatever order you get, you are going to push it onto it, right? So whenever you visit, see, I am traversing the tree top to down, left to right, and while traversing, whenever I visit a node, it means that if that node is function call, I'm going to push a stack record, and if that node is some other thing, I'm going to execute that instruction. So first thing is, when I'm traversing, I'll come across a of 3, therefore I'm going to push a of 3 onto the stack. And next thing is, I'll see a of 2, therefore I'm going to push a of 2 onto the stack. And next thing is a of 1, therefore I'm going to push a of 1 onto the stack. And next thing is a of 0, so a of 0 is also pushed onto the stack, right? And now I'm going back. So this is the last time I'm going to visit a of 1. So whenever it is the last time you are going to visit a node, if that is a function call, then you try to pop it off. See, this is the last time I'm going to visit a of 0, therefore you pop it off, which means a of 0 is popped off without printing anything. The reason is, this is the reason, if n is greater than or equal to 0, since a is not greater than 0, it is not useful, right? It is not doing anything. It is simply pushed onto the stack and it is simply popped off. So this, this pushing and popping is just a time waste. So if you want to optimize it, even if you write it as if n is greater than 1, then only you can go inside, otherwise you need not go inside. Okay, now next thing that you come across is printf1, therefore print 1 is printed. So what is the program that is being, that is on top of the stack is a of 1, which means you are at this point. In a of 1 you are at this point and 1 is printed. And next one, see, this is at this point you are going to leave 1. So whenever it is the last time you are going to visit a function call, you pop it off, therefore a of 1 is popped off. And what is reached? A of printf2, therefore 2 is printed. And now this is the last time I am going to visit a of 2. So whenever it is the last time you are going to visit any function call, pop it off. A of 2 is popped off, and what is printed? 3. And this is the last time I am going to visit a of 3, therefore a of 3 is popped off, right? Then how to analyze the space complexity in this case is, we need not analyze the space complexity by counting the number of extra variables, right? So in this case there are no extra variables also, but we have to analyze the space complexity depending on the depth of the stack or height of the stack. So how many stack records are required? So every stack record is going to occupy a constant time. Let us say the space required by every stack record is k cells, right? And now how many such k's are required? Number of recursive calls. So if the input is n, then the number of recursive calls required are n plus 1, and every recursive call is going to take k cells. Therefore the total space required for this algorithm is k into n, order of k into n. Since k is a constant, you can even say the total space required is order of n, right? Why? Because at any time I need a maximum. The stack is growing till this point, right? It is not growing beyond this. Therefore the space required is order of n. What about the time required for this algorithm? So time required is, so did you understand how to print this? I'm just writing the tree and then traversing the tree top to down, left to right, and whenever any node is visited, if that node is a function call, I'm going to push a activation record, and if the node is some other instruction, I'm going to execute it. And whenever I'm seeing a node for the last time, if it is the last time I'm visiting it, a function call, then I'm going to pop it off. Then I'm going to see how big the stack is going to grow. That is nothing but the space complexity. Therefore in this case the space complexity is order of n. Then what about the time complexity for this? In order to analyze the time complexity, you might have to write the recursive equations. Why? Because recursive functions are solved using recursive equations. So see this, let us assume that for this a of n, the time required is t of n. If the time required is t of n, then what is the doing? In order to solve a of n, time required is t of n, then it is going inside and then it is solving a of n minus 1. If the time required for a of n is t of n, then what will be the time required for a of n minus 1? It will be t of n minus 1. Therefore in order to solve this, I have to solve this. So t of n equal to t of n minus 1 plus printing action is going to take some constant time, for which either you could write k or 1. That is fine. So 1 or k, it is not an issue because it is going to be a constant time. Now you have to analyze this recursive equation so that you could find out the time complexity. So one way to analyze this recursive equation is, this is not in the form where you could apply Master's theorem. Therefore you go with back substitution. So what is back substitution? T of n minus 1 equal to T of n minus 2 plus 1. Then what is T of n minus 2? T of n minus 2 equal to T of n minus 3 plus 1, and you keep on substituting it backwards. Then what do I get? T of n equal to, in place of T of n minus 1, if you substitute this entire thing, we are going to get T of n minus 2 plus 1 plus 1. See, in place of T of n minus 2, I am substituting this entire thing. That is why I got it. That equal to T of n minus 2 plus 2, right? And now in place of T of n minus 2, you substitute this, which means T of n minus 3 plus 1 plus 2, right? That equal to T of n minus 3 plus 3. So on, what do I get? T of n minus k plus k. Then where are you going to stop this? Whenever n is 0, whenever n goes to 0, then it is going to stop. So right, so this recursive equation is, this is when n is greater than or equal to 1, right? And this is 0 when n equal to 0. So how to make this one 0? Whenever k equal to n, it is going to be 0. So substitute in place of k, you substitute n. Then what do I get? T of n minus n plus n, that equal to T of 0 plus n, that equal to, whenever it is whenever n equal to 0, it is going to be, let us say instead of 0, it is going to be 1. The reason is, you have to check if n is greater than or equal to 1. At least for this comparison, you are going to take one time. Therefore, let me write T of 0 equal to 1. So it is order of n. So the time complexity required for this algorithm is order of n, as well as the space complexity required for this algorithm is order of n. So some interesting questions about recursive programs is, one is they will ask you to find out the time complexity, second thing is they will ask you to find out the space complexity, and third thing is they will ask you to find out how many times this a has been called. So in this program, if there is n, then n plus 1 times a is called, and all of them are required simultaneously, right? That is why the height of the stack is maximum n, right? So it is maximum n plus 1. So assuming that every stack is going to take k cells, the total space complexity is order of n, and the total time complexity is order of n. We shall see one more example about this. Now I'll take a bigger example and I'll analyze how to find out the time complexity and space complexity. Say the program is this: a of n, if n is greater than or equal to 1, then I'm going to call a of n minus 1 and then printf n, and again I'm going to call a of n minus 1. So two times I am going to call a of n minus 1. Okay. So in this case, what is the total complexity, space complexity and time complexity? So how to analyze this? Since the number of lines are very less, it is always better that you go with the tree method. So once you go with the tree method, then you build the stack and you understand how many, what is the depth of the stack, then you can find out the space complexity. So let me take a small example. Let me say I have to trace it out on a of 3. Okay. So if I have to trace it out on a of 3, see this, a of 3, a of n is going to call a of n minus 1 and then printing n and then a of n minus 1, which means a of 3 is going to call a of 2 and then printf 3 and then call a of 2. And then again a of 2 is going to call a of 1 and then printf 2 and then a of 1. The same thing is happening here, right? A of 2 is going to call a of 1 and printf 2 and a of 1. And what about a of 1? A of 1 is going to call a of 0, and then printf1 and a of 0. And what about this a of 1? It is going to call a of 0 and then printf1 and then a of 0, right? So I think this example is a bit bigger, so let me take it with a of 2 and I'll explain you, then we can go with a of 3, or okay, we can continue with this. A of 2, then let me say a of 2 is a of 1 printf2 a of 1, and again a of 1 is a of 0 printf1 a of 0, and a of 1 is same a of 0 printf1 and a of 0, right? So this is how the tree has grown, right? So one thing is, how in order to compute this a of 3, how many total how many times a is called? So that question could be asked by counting total number of a's: 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, which means in order to solve the question with a of 3, the total number of recursive calls or total number of times a is called is 15 times. Okay, and what about if I have to solve a of 2? If I have to solve a of 2, the total number a of 2 means either you can count this subtree or this subtree, right? Because it is starting with a of 2. In order to count a of 2, what is happening is so 1, 2, 3, 4, 5, 6, 7 times. And in order to solve a of 1, how many times a is called is a of 1, 1, 2, 3, right? So you should understand some pattern here. So the pattern is, it is nothing but a of 3 plus 1, 2 power 3 plus 1 minus 1. This is nothing but 2 power 2 plus 1 minus 1. This is nothing but 2 power 1 plus 1 minus 1, right? Therefore, if I have a of n, then the number of recursive calls required is, or the number of times a is called in order to solve this problem is 2 power n plus 1 minus 1. So these many recursive calls are required. So now if these many recursive calls are required, does it mean that the space complexity is order of 2 power n plus 1? That is an interesting question, right? See, I know that the total number of recursive calls required in order to solve this question is order of 2 power n plus 1. But does it mean that I need a stack which should have a maximum depth of 2 power n plus 1? It turns out that it is not the answer. Number of recursive calls are definitely 2 power n plus 1, but the amount of space required is not 2 power n plus 1. The reason is this. Let's see how the stack works. What is being pushed onto the stack and what is the output. So let's trace it out. So I am going to start with this. I'll be standing here. So whenever I visit any node for the first time, if this is a function call, you are going to push it onto the stack. So since that is a function call, what will be pushed onto the stack? A of 3, right? And then this is a function call, again a of 2 is going to be pushed, a of 2, and again a function call, a of 2 is going to be pushed, a of 1 is going to be pushed, and again is a function call, therefore a of 1 is going to be pushed, a of 0 is going to be pushed, right? But now you should understand that after this a of 0 is visited for the last time, which means this is going to be popped off, right? So at this point we are going to how much level? 3 plus 1, which is 4, right? We have grown this stack to 4, and from there on we are reusing the same space, which means by the time I reach here, I am going to pop a of 0. Therefore the stack contains only 3 elements. I don't think that the stack requires more than these 4. See this? Now next thing is printf 1. Therefore output, in the output 1 is printed, and then a of 0, again a of 0 is called. This is the second a of 0, right? This is second a of 0. Therefore at this point again a of 0 got emptied, which means this cell got emptied. Why? A of 0 is called and it is simply popped off. And now this is the last time A of 1 is visited. Therefore, A of 1 is also popped off. See this? Now we are never going to grow beyond these 4 cells. We are going to use only those 4 cells. Now printf 2. Therefore, 2 will be printed. And now A of 1 is called. Why? Because this is the first time I am visiting A of 1. Therefore, you push A of 1 onto the stack. So A of 1, this second A of 1 is actually occupying the same cell which was occupied by the first A of 1, right? And now A of 0 is called. Therefore, this is the third A of 0 which is actually occupying the same cell as A of 0 and A of 0, the previous two A of 0s, right? And now printf 1, which means 1 will be printed. And now at this point A of 0 has to be popped off. Before printing 1, A of 0 has to be popped off, right? And now I am coming across the next A of 0. Therefore, you push A of 0, right? And at this point A of 1 is being visited for the last time. So what should you do? Pop off A of 0. So A of 0 is popped off and A of 1 has to be popped off. At this point A of 0 has to be popped off, and at this point A of 1 has to be popped off. So again A of 0 and A of 1 cells, they got emptied. Now this is the last time I am going to visit A of 2. Therefore pop off A of 2 also, right? And now you are going to print 3. So 3 will be printed. Now you are going to see A of 2 for the first time. Therefore you print A of 2 onto the stack. And then you are going to see A of 1. Therefore you push A of 1 onto the stack. And then you are going to see A of 0. And now you push A of 0. See this? A of 2, this is the second time we are calling A of 2. It is occupying the same cell which was occupied by the previous A of 2. Therefore, all the function calls which are at the same level are actually occupying the same cell one by one, right? And now it is A of 0. So A of 0 is being pushed. And this is the last time A of 0 is visited. Therefore, pop off A of 0. And now you are visiting printf 1. So print 1. And now you are visiting A of 0 again. Therefore you push A of 0. And now this is the last time A of 0 is visited. So you pop it off. And this is the last time A of 1 is visited. So you pop it off. And this is the first, and this is again you are visiting printf 2. Therefore printf 2. This is the first time you are visiting A of 1. Therefore you push A of 1. And this is the first time you are visiting A of 0, so you push A of 0. Last time you are visiting A of 0, pop it off. Printf 1, done. And then A of 0 is again visited, therefore push A of 0. And A of 0 is visited last time, therefore pop it off. And now A of 1 is visited last time, pop it off. A of 2 is visited last time, pop it off. A of 3 is visited for the last time, therefore pop it off. So even though the number of function calls required are 2 power n plus 1, actually the stack required only n plus 1 cells, which means in order to execute A of 3, I needed only 4 cells or 4 records in the stack. So assuming that every record is of constant space k, if I have to execute A of n, I don't need a stack of more than n plus 1 size, and every record assuming that is taking k, the total space required for this program is again like the previous one, order of n into k, which is nothing but order of n. Okay, so k is a constant, therefore you can directly write it like this. So one thing you should observe is, even though the number of recursive calling of the functions are more, it doesn't mean that the space required by this recursive program is more. The reason is the number of the function calls are actually occupying in some order. See, in this first level always A of 3 is present. In this second level, always a of 2 is present. In this third level, always 1 is present, and in this fourth level, always 0 is present, which means whenever a of 0 was on the top, no other a of 0 was called. Therefore, once it gets vacated, then only the second a of 0 is coming and sitting here. All the a of 0s will reach this cell, and all a of 1s will reach this, and all a of 2s will reach this, all a of 3s will reach this. Therefore, even though the number of recursive functions required is, recursive calls required is order of 2 power n plus 1 or order of 2 power n, the total space is. So you see this pattern in this program. There are some patterns which are repeating again and again, which means if I have this part a of 2, so a of 2 is printing this, isn't it? This is printed by a of 2, and then I am printing this part 3, and then again I am calling a of 2, which means a of 2 is again printing this, right? So a of 2 is, actually the work done by a of 2 is same. So whenever you execute this a of 2, it will always print the same. Then why should you execute it 2 times? So what you could do is, whenever there is some part of the program or the part of the problem which is repeating over and again and without doing any much difference, then you could execute it 1 time, and second time whenever you are actually calling, you could actually save the result and type it out, which means if you see this, whenever a of 0 is called, it is doing nothing, right? And whenever a of 1 is called, it is printing 1, and whenever a of 2 is called, it is printing 1 to 1, and whenever a of 3 is called, this entire thing is repeated, isn't it? Then what you could do is, instead of running this over and again, you could make some modifications in the program in such a way that already if you have computed it once, you could save it somewhere in some table, and then you could reuse it again and again, which means dynamically I'll decide whether to execute the program again or not. If the result is already computed and it is available, I'll dynamically decide that I'll not execute it again. If the result is not available, I'll dynamically decide that maybe I have to execute it again. So what that method is called is dynamic programming. So for this problem, if I apply dynamic programming, I could save the results of already computed subproblems in a table, and then I could print them later, which means, see this. So initially I know that the total number of function calls are a of 3, a of 2, a of 1, a of 0. Therefore, I'll write a of 3, a of 2, a of 1, a of 0, right? Then I'll go like this, go like this, go like this. So whenever a of 3 is called, I'll decide whether I should call it or not. So since a of 3 is first time called, I have to call it. Since a of 2 is first time called, I have to call it. Since a of 1 is first time called, I have to call it. And then a of 0 is first time called, I have to call it. Therefore, a of 3, a of 2, a of 1, a of 0, this first chain, they have to be definitely called. And then I'll decide, by the time I finish a of 0, I'll see what a of 0 is doing. A of 0 is not printing anything. Therefore, I'll save in the table that a of 0 is not printing anything, right? And by the time I reach this point, I'll know that a of 1 is printing 1. Therefore, for a of 1, I'll note down that it is printing 1. And now when I have to print 2, I'll print 2. But when I come to this point, this second time a of 1 is not required. The reason is, first time a of 1 has printed 1. Therefore, I know that it should print 1. So without calling a of 1 again, I will not do this entire procedure. That is called dynamic programming. This entire part is not required, and this a of 0 is not required. And by the time I reach here, I would have already known the result of a of 2. So I would have already known the result of a of 2 is 1 to 1. Therefore, by the time I reach here, I will not execute this entire part, right? So using that, I could actually decrease the time complexity. So whenever the subproblems are repeating, you could compute the subproblem once, save the result in the table, and you could again reuse it. So if I use that kind of tabularization, which means inside the table, if I save the computed results and then use them later dynamically, then that is called dynamic programming. So all the problems are not eligible for dynamic programming, only the problems in which the subsequences are repeated, such problems are eligible for dynamic programming. So using dynamic programming we can decrease it later. So I'll show you about the dynamic programming at depth later. Here my intention is to compute the space complexity, and we have seen that the space complexity is order of n. Now let's see how to, what is this time complexity here. So one thing is, number of function calls required without dynamic programming is order of 2 power n plus 1. With dynamic programming is order of n, isn't it? Then without dynamic programming, the space complexity required is order of n. With dynamic programming, the space complexity required is, I might have to have a table, and in that table I might have to save the outputs. Therefore this space has to be included. But without dynamic programming, if I use only the stack, then the space complexity is order of n, right? So anyways, if that program is executed without any modifications in the program, without writing any snippets here, or without using any table, the number of recursion calls is order of 2 power n plus 1, and the time complexity is, space complexity is order of n. And now let's see the time complexity. So in order to see the time complexity, we might have to write the recursive equation. The reason is the program is recursive. So since the program is recursive, I am going to use recursive equations for this. So let us assume that time taken to solve this problem is t of n. Then what will be the time taken to solve this problem? T of n minus 1. What will be the time taken to solve this problem? T of n minus 1. And to print it, let me say there is constant time. Either you can write k or 1. Therefore total time taken to solve the problem, T of n, is equal to 2 times the time taken to solve T of n minus 1 plus 1, right? Now you can use the back substitution method and you can find out the solution for this. How to use the back substitution method is, so one thing is, you understood that T of n equal to this, then what is T of n minus 1, and where are you going to stop? We are going to stop, so time complexity is 0 whenever, or time complexity is constant whenever n reaches 0, and this is whenever n is greater than 0, which means greater than or equal to 1. So whenever n is greater than or equal to 1, this much time is taken, and whenever n equal to 1, this much time is taken, right? So now let's see the time complexity. T of n minus 1 equal to, in place of T of n, I am substituting T of n minus 1. Then what will this be? 2 into T of n minus 2 plus 1. Then what will be T of n minus 2? T of n minus 2 will be, in place of n I am substituting n minus 2. 2 into T of n minus 3 plus 1, right? And you keep on back substituting them. Then what do I get? T of n equal to 2 into, I have to substitute this entire thing in T of n minus 1. And what do I get? 2 into T of n minus 2 plus 1 plus 1. That equal to 2 square into T of n minus 2 plus 2 plus 1, right? And now in place of T of n minus 2, you substitute this. Then what do I get? 2 square into 2 into T of n minus 3 plus 1 plus 2 plus 1. I am just substituting it, backwards. How did I get this? By substituting in place of T of n minus 1, I am substituting this entire thing. And then how did I get this? In place of T of n minus 2, I am substituting this entire thing. It is called back substitution, right? So what do I get here? 2 cube into T of n minus 3 plus 2 square plus 2 plus 1, right? Then how can I generalize it? It is 2 power k into T of n minus k plus 2 power k minus 1 plus so on plus 2 square plus 2 plus 1, right? Now when are you going to stop it? I am going to stop it whenever this entire part is going to be 0. So when will this entire part be 0? Whenever n equal to k, right? Therefore in place of k, you substitute n. Whenever k equal to n, this entire part is going to be 0, and that is nothing but 1. Therefore in place of k, you substitute n. Then what do I get? 2 power n into T of 0 plus 2 power n minus 1 plus 2 power n minus 2 plus so on plus 2 square plus 2 power 1 plus 1. Then what do I get? 2 power n plus 2 power n minus 1 plus 2 power n minus 2 plus so on plus 2 square plus 2 plus 1, right? Then if you add this all, it is nothing but GP. Then you are going to get order of 2 power n plus 1, right? So that is what you are going to get, which is nothing but order of 2 power n, which is exponential time. So the time complexity required to solve this question is very high. The reason is you might have to execute the entire tree, right? And the tree is kind of simple. We have to traverse the entire tree, and the tree is actually containing order of 2 power n plus 1 number of nodes. Therefore, I know we have to at least visit every node once. Even if you think that the time is constant to visit a node, the total time taken is going to be order of 2 power n, but the space complexity is going to be order of n, right? So if you have to decrease either the space complexity, either this time complexity or the number of recursive calls, the best method is save the results and then use them without actually performing the computation. That is called dynamic programming. We shall see more about dynamic programming when we go to the topic. Here my intention is to solve only the time complexity and space complexity of a recursive program, right? And now that you understood how to use the recursion, okay, this recursion part, let me go to some other programs, both iterative and recursive programs, and I'll show you how actual sorting and searching programs. Okay, fine.